Okay, so thank you, Alan, for the introduction. Um, thank you so much, everyone, for coming to my talk. I will talk about these Supercatline numbers and their clearest connection to the problem of summations, Fourier summations over finite fields. And the bridge to those two things is this phenomenon of geometry. Okay, this is joint work with my supervisor, Norman Wahlberger, who I observe is in the audience. So hi, Norman. And fingers crossed, this will be my last talk in the Postgraduate Conference. So looking forward to just finish the thing with flying colors, hopefully. Okay, so let's have a look at the problem we have here. So we want to make sense of an integration theory of polynomials over the unit circle when the underlying field is finite. Okay, this is very much a problem of Fourier analysis. In the classical sense, if you're given a function, you want to expand that as Fourier series. What you want to do, the tool you want to have is the technology to integrate over the unit circle. Okay, but in this case, because this is finite field analysis, this will be a foundation of Fourier analysis for finite field, but the functions will take value in the field itself. So this is different from the classical approach that the functions are complex value in the classical sense. So the domain is still, it's probably finite field, but then like the value is assumed to be complex numbers. Okay, in this case, we don't want that. We really want to work just with that finite field. Okay, and then we are considering not just the Euclidean geometry, okay, but also the non-Euclidean geometry. And actually the geometries that we are considering, there are 3 in total, they are intricately connected. Again, this is a phenomenon of geometry. Right, now let's have a look at what the Supercatline numbers are. Okay, so the Supercatline numbers are integers of this form. Okay, it's parameterized by 2 non-negative integers m and n. And then curiously, this is always an integer, which means that this family of numbers, family of integers has some combinatorial interpretations. And there are some given in terms of Poisson trees or cubic trees, tuples of like paths satisfying certain conditions, Motzkin paths, and one that will be prominent in our analysis is one interpretation by Georgiades, Muramasa, and Tanaka, okay, in terms of lattice paths. So before we go into that more deeply, this is a table of our Supercatline numbers. You can immediately see that in this table, there is some symmetry property. And furthermore, if you look at the 0th row and the diagonals as well, they are the central binomial coefficients. Okay, and the first row, they're twice the Catalan numbers. Okay, they are central in combinatorics. Okay, so what does that identity by Georgiades, Muramasa, and Tanaka have to do with our analysis? So they discovered that Supercatline numbers can be represented as certain values of what's called Kraftcheck polynomial. Okay, I won't go into detail about like what it is, but it is playing quite a role in field of combinatorics, harmonic analysis. Okay, but one consequence of that observation is the fact that if I have this one integer polynomial, 1 plus alpha to the 2m and 1 minus alpha to the 2n, okay, and I extract that central coefficient, so coefficient of alpha to the m plus n, so up to some sign, this will be exactly the Supercatline numbers. Okay, that's very nice because yeah, it's given as some coefficient of certain quite simple polynomial. Okay, that's good. But then our main object really is not the Supercatline numbers themselves, but rather circular Supercatline numbers. Okay, so it's still a family of numbers, now rational. Slightly tweak from the Supercatline numbers. You have this extra 1 on 4 to the m plus n appearing there. So two observations come to mind. First is that if I have an odd prime p, the reduction of this rational number modulo p is always well defined. The reason of that is that this SMN is always an integer. Okay, the numerator is always an integer and the denominator is never a multiple of p. Okay, so that reduction is always well defined. And furthermore, connecting this story to the previous coefficient picking problem, I can just simply divide everything by 2 to the 2m, 2 to the 2n. Okay, so I have this now rational polynomial and our circular Supercatline numbers. Omega mn is just the coefficient of that central term of rational polynomial. Okay, so this is some values of omega mn. You can observe that it's still retaining the symmetry property, and then that there is this like sort of Pascal-like property that, you know, if you have a look at the red entry there, it's precisely the sum of the entry to its right and the entry just below that. Okay, so it's quite nice, and it's true for any entry. Okay, so let's have a look at our setup here. So we are going to work with finite field of size q, where q is a power of some odd prime p. So we can impose some geometry to this setup by introducing some invariable symmetric matrix M. Okay, and of particular interest are three special matrices I, J, and K. So the matrix I will give rise to the usual Euclidean geometry, which I will call the blue geometry, and the J and K matrices will give rise to the non-Euclidean geometry, which I will call the red and green geometry respectively. Okay, so in that setup, I have three different unit circles. Okay, so there is this subscript of G, subscript of R, and subscript of P to indicate green, red, and blue. Okay, so we have these three unit circles in its geometry. Okay, and especially in the blue geometry, that's the most complicated geometry among three geometries, there is a slight distinction whether -1 is a square or not. So we want to capture that. So first we recall the Legendre symbol. Okay, if I have an odd prime p, -1 over p there is a symbol whether it's 1 or -1. It's 1 if -1 is a square, and -1 if it is not a square in our prime field of p. And for general prime power q, then the Jacobi symbol is introduced. It's really an analog of the Legendre symbol. Okay, so we can immediately observe one lemma regarding the size of the unit circles, that the size of the green and red circle is q-1, but then the size of the blue circle is going to be either q-1 or q+1, depending on the size of, depending on whether -1 is a square or not in our field. Okay, so we are going to talk about this notion of circular integral functional phi. Okay, so domain is like vector space on the algebra of polynomials in two variables alpha and beta, and the value is in the field itself. So we call this phi circular integral functional precisely when phi satisfies three conditions. The first one is just that normalization condition, that the polynomial 1 is mapped to 1 in the field. Okay, and then we have this locality property that if you have a function or polynomial in this case that restricts to 0 on the circle, whatever a circle is, then the integral is 0. Okay, and then there is this invariance condition that, well, basically it's saying that your integral should be invariant under rotation and reflection. Okay, that's to be expected from the integral in the classical sense. Okay, so we're not really deviating a lot from that classical theory. Okay, so, well, the most natural candidate for our integral in its geometry is basically just this psi, which is basically a linear functional that maps f, like a polynomial f, to, well, you evaluate f on any point on the circle and then take the sum. Okay, that's one candidate. But curiously, there is minus sign in front, and especially in the blue case, there is -1 on Q with Jacobi symbol here, and they're just there to make sure that these three psi's satisfy the normalization condition. Okay, but then one of the main results in our study here is that we can show that these psi are the unique circular integral functional in its geometry. Okay, and this is done usually in two steps. First, that these psi's do indeed satisfy the three conditions. That's easy. And then what's slightly harder is to show that if such a psi, such a phi exists, then it must be unique. Okay, these two steps will ensure that our psi here is a unique circular integral functional. Okay, but that's not the main point of our talk. Okay, that's one thing. That's like one topic already to talk about, but that's not the highlight of this talk. The highlight of this talk is to give an explicit formula for the psi sub g, psi sub r, and psi sub b. Okay, well, let's have a look at the situation in the green geometry. Okay, and it's the simplest geometry among three because, you know, the unit circle parameterization is very easy. You have this xy equals 1, so, well, y is 1 on x. It's as easy as that. So in this green geometry, this psi of alpha to the k, beta to the L is either 1 or 0, and there is this divisibility condition appears. And I should probably preface that by saying that, well, because of linearity, we can just consider the monomials, alpha to the k, beta to the L. Okay, the proof for this is not that hard to derive because, well, you can observe that our psi sub g is basically just summing powers of x, where x is in our multiplicative group in our field. Okay, and that's quite standard, that the value is going to be 1 or 0. Okay, but this is actually fundamental because the results in the green, the result in the red and blue geometry will stem from this nice little formula. So let's have a look at the situation for the red geometry. So for the red geometry, and maybe the blue one as well, we have to work with this family of polynomials f sub kl, which is similar to what you've seen before. So now I have this the powers of 1 plus alpha on 2 to the k, and then the powers of 1 minus alpha on 2 to the l. Okay, so this theorem here is saying that, well, in the red situation, if I want to integrate alpha to the k, beta to the l over red geometry, all I need to do is associate to this monomial a rational polynomial f sub kl, and take some particular coefficients of some power. Okay, take the sum and then reduce that modulo p. As easy as that. Okay, that's if all the powers are even, but then if one of them is odd, then it's already 0. Okay, and then in the formula you see two sort of like constants w and r, and they are really you can think of them as geometric constants that depend on the size of the circle. Okay, so what's the situation in the blue geometry? Well, the situation is pretty much the same, except that now you have this -1 to the n in front of a f sub kl. Okay, it's exactly the same. Okay, but then I want you to notice that, well, this is very similar to the red situation, but there is actually an implicit appearance of the Jacobi symbol in the formula. Why is that? Because we have this geometric constant W and R to depend on the size of the circle. Okay, but then the size of the blue circle is, well, Q minus it is Jacobi symbol. Okay, so there is this nice dependency here, and we can actually combine them into one single formula. That's quite neat. Okay, so we can reduce this to the circular Supercatline numbers. I must say that the title on this slide should have been omega for circular Supercatline numbers, not CS. That was my previous notation. Yeah, but then what it's saying is that if your degree is small enough, in this case less than Q minus 1, then in both red and blue situation, your R is going to be 0. Okay, so in this case, this expression on the left-hand side just reduces to one single term. Okay, where the power of alpha that you're interested in is m plus n. So that's just simply the circular Supercatline numbers up to some sign. So we have this like nice reduction theorem that if your power of monomial is less than Q minus 1, then in the blue situation, just really have the circular Supercatline numbers, but in the red situation, you have this -1 to the n. Okay, so let's have a look at some examples, because it's best illustrated by some examples. So say I have my power on my prime to be 13, so my field is of size 13. So in this case, -1 is a square. Okay, -1 is 12, which is 5 square. So -1 of for Q, that should have been 1, not -1. I'm sorry about that. So the size of the blue circle is 13 minus 1, which is 12. You can see that the blue circle is just that point. Right. So in particular, if I have this alpha to the 4th beta square to integrate, power is small enough. So all I need to do is just consider omega 2, 1. Okay, that's 1/16 up to some sign. Then reduce that modulo 13. Really, that's the whole thing. Okay, that's going to be 4. What about like, higher degree? So K is 8, L is 6, then you have this W and R, you can compute them to be 6 and 1 respectively. So if I want to integrate alpha to the 8, beta to the 6, then you have this, all I need to do is consider F8 6, which is this 1 plus alpha on 2 to the 8, 1 minus alpha on 2 to the 6. Okay, that's a polynomial of degree 14, but I am interested in just 3 of those terms, which are the coefficients of alpha to the 7 and alpha to the 13. And after, if some computation, take the sum, reduce that modulo 13, and that's going to be just 9. Okay. So you can observe that the middle term corresponds to the circular Supercatline numbers, omega 4, 3. Okay. So let's have a look maybe at one more example where maybe the size of the field is not a prime number, but rather a power of prime, K5 square in this case. So we can identify F25 as A plus B omega, where omega square is 2 because alpha square minus 2 is irreducible in this F5 upon omega. Yeah, so I have this red circle, okay, of size 24. So now if my power is big enough, say 30 and 24, then I don't have to painfully compute, like take the power of 30 and then take the sum, and then there are 24 terms that's going to be appearing there. But rather I can just consider this polynomial f3024 and just take suitable powers of alpha and the coefficient of that. Okay, in this case there are 5 terms to consider. Take the sum, reduce that modulo p is 5, and then I have 2. That's very nice. Okay, it's very simple. And again, the middle term corresponds to omega 1512. So really, what does this mean? Well, now we have this curious connection between the problem of summing polynomials over finite field to the problem of just basically picking coefficients and take the sum. Okay, summing polynomials to summing coefficients of some polynomial. That's very like, to me, that's almost like magic. Okay, it's actually simple enough, and the result in the green and then the red and then the blue are pretty much connected. Okay, so this means that, well, we can now set up some sort of Fourier analysis for a complex valued function, but now say the complex value in a sense of extension of field itself. Okay, rather than the usual complex numbers, if -1 is not a square, or perhaps this complex valued function. So when the domain of the function is maybe the red circle, but then we're not considering the usual complex valued extension, but rather this sort of thing called the red complex numbers, or sometimes called split complex numbers. So there are definitely plenty of possibilities to consider here. Okay, and some further readings to consider, want to have a look, and thank you so much. I'm gonna stop recording now.